Welcome back to ECE 320 after, I guess, a stressful spring break, according to some, because of nervousness over the exam. We'll return that at the end of class. Oh, that got picked up on the audio, I'm sure. What I want to do today is make clear where we're headed. There should be a lot of new material on the website if you are keeping track of that. And that is pertaining to unit number 7, which is beyond where we are now. You should be, your next homework assignment should be coming from homework number 6, or unit number 6. And that will be on the material we're talking about today, which is S-domain circuit analysis, initial value theorem, and final value theorem. One thing that I want to make clear is that a week from today you do not have to come to class. I won't be here, or I don't know if I will be here or not, so I'm not even going to stress it. That's why the material is posted online, and you can then look at that convolution material on D2L. That's in unit number 7. And all of that then should guide you through the motivation of convolution, the introduction to convolution, flip and slide, limits, and what's the other one? Intervals and limits, I believe, is how I've labeled the other. And then a few examples illustrating convolution. Hopefully that will be clear to you. There are notes and videos for that material on unit number 7. And we will post this material under unit number 6, which is concerned with homework number 6. And because we will not meet a week from today, that won't be due until the next time we meet. So you don't have to worry about coming in if that day off allows you to not have to worry about rushing around to this particular location. That's due then a week from Thursday, homework number 6, but we should be more than farther than that along in the material. It's just that we're turning it in a little after it's been presented in class. Today what I want to do, are there any questions on where we're going? So we're going, and I haven't yet decided what we'll do with Unit 8, but it will either be Bode plots or probably filter design, maybe with passive filter design. That I haven't decided which way we will go at that point. Question? And we'll try to get into active filters. And so learning the passive filters, then the active filters, you'll have one of your problems, I believe, either on homework 6 or homework 7, does deal with an active device. So you will get some analysis on that, hopefully. Other questions? With what? We probably will not. I'm assuming that once you have the dot convention in hand, you can then apply that to a transformer problem if you needed to using Laplace transforms. So we will try to make sure that it's clear how to attack problems in the S domain that right now are going to be mostly restricted to passive elements, R's, L's, and C's, but we will have one problem that you're deriving the equations for the governing dynamics with an active element, but it's surrounded by passive elements, R's, L's, and C's. And that's what you'll be using in the S domain to derive your governing equations, or equations of motion. And after this material that we get today, if we get that far, we'll start immediately into transfer functions, which is what we're ready to be doing. And once we have transfer functions in hand, we should be able to move into whichever direction we want, either Bode plots, passive, active filters, etc. And then we hope to finish with two-port devices. That's the rest of the semester in a nutshell. And we're, according to the homework, we're halfway there. In timeline, we're more than halfway to our destination. And you've already had 2 of the exams. Let's then talk about the initial value theorem. Last time we covered the final value theorem, and I'm sure that you all remember that after a nice, restful spring recess. Here's the initial value theorem. It has the same kinds of conditions or constraints. First, we want x to be well behaved, which we are saying that by saying we want x of t and its derivative to be able to or have a Laplace transform. And I will state that by saying if 1, x of t and x prime of t, the derivative of x, are Laplace transformable, and 2, this limit as s goes to infinity of s, x of s, all we need for now is for that limit to exist. Then we can apply the initial value theorem, meaning we don't need to check the location of the poles of s, x of s to apply the initial value theorem. All we have to do is see if this limit exists. If it does exist, then we can apply the initial value theorem, which says that now the limit as t approaches 0 from the right, or as t goes to 0 plus, of this waveform x of t, that's found or can be shown to be equivalent to the limit as s goes to infinity of s, x of s. Meaning we're looking at this limit in just the opposite direction that we were looking at the final value theorem. Since we are on the left-hand side looking at the opposite limiting case there as well. Let's look at some examples. And I may just not look at the proof because the proof is very similar to the other one. You simply break up the integral into a couple of pieces. But let's look at the following. Suppose that you've performed analysis on your circuit and found that capital V sub 0 of s, maybe that's the Laplace transform of some output voltage, is minus 4 2s squared plus 3s plus 1. And we want to know then what's the limit as t goes to 0 plus of the time domain waveform V sub 0 of t. That's then the limit as s goes to infinity of s times, V sub 0 of s, which that's going to be the limit as s marches off to infinity of minus 4s over 2s squared plus 3s plus 1. Pardon? I buried the s in there already. So we have s times v naught of s, and now we are looking at the limit as s marches off to infinity. And how have we looked at this in the past? When we were finding our partial fraction expansions, this was one approach to try to find one of those coefficients. We multiplied through by s and let s go to infinity. In this case, we're really looking at the highest powers of s in the numerator and the denominator and looking at that ratio. In this case, we effectively have minus 2 over s, as s goes to infinity. And that, I hope you see, is 0. Meaning this particular waveform started its path in time at the origin, or at a value of 0. Let's look at another example. And hopefully these are not anything too foreign. We now look at the limit. Well, one thing that we will want to start doing is getting more comfortable with talking about poles and zeros. This is now already in factored form, this transform for x, or capital X of s. Where are our finite zeros? Do we have any finite zeros in capital X of s? We have a finite zero at s equal minus 1. Do we have any finite poles? We have one at the origin and one at minus 2. And those images of x's and o's in the left half plane, or on the complex s plane, will help us when we start talking about Bode plots in terms of understanding what's happening or what's going to happen. But for now, we want to apply the initial value theorem. We are now saying that we have this limit as s goes off to infinity of s times x of s, which now becomes, canceling the s in the denominator with the s in the numerator, we now have s plus 1 over s plus 2. And what does that say? Or what's that limit? That's 1. We have monic polynomials in the numerator and the denominator, and so their ratio is 1 over 1 as that same power of s marches off to infinity. Meaning this particular time domain waveform started at 1. What about the next example? Suppose that we are given y of s is s over s squared plus 4. If I ask you what that was as a time domain waveform, even after a long spring break, I hope you can tell me what that is since you're still in ECE 320. What's y of t? Okay, at least that's the main thing. Somebody said it's a sine or a cosine, and how do you know that? Because you can look at the denominator and see that you have purely imaginary roots. You now have poles at plus and minus j2. Those are right on the imaginary axis. So independent, if I covered up the numerator, you wouldn't know whether that was a sine or a cosine. But because of this specific structure of y of s, or the numerator, what do you know this is going to be? This is going to be a pure cosine. If I had something like 2s plus 7 in the numerator, now it's some combination of sine and cosine. Is everybody okay with that? If I had simply a constant in the numerator, it would be a pure sine of some magnitude. Here I simply have a linear polynomial in s with only the linear coefficient there, s. And now, what's the magnitude of this cosine waveform? It's right there, isn't it? Which is implicit, but we now know that that's cosine, the frequency. And we are dealing with one-sided transforms. This then cosine turns on at time t equals 0. And I can show that by multiplying it or switching it on with u of t. If we simply apply the initial value theorem, and this one we better know what it looks like at time t equals 0. What's a cosine at 0? 1. So we know a way to check this. Let's now see if our initial value theorem actually comes back with the correct result. And like before, we now look at the leading powers of s in both the numerator and denominator and look at their ratio. We have s squared over s squared, and that's going to march off to infinity, and the top and bottom equally or in the same way, and so their ratio is now 1. Questions on that? That should not be that difficult, especially the initial value theorem is easier to apply than the final value theorem. Final value theorem, remember, you need to check. You need to check what? You need to check the poles of s, capital X of s, and where do you want those to not be? They cannot be on the imaginary axis, and they cannot be in the right half plane. If they are on the imaginary axis or in the right half plane, you cannot use the final value theorem. Questions on final value theorem or initial value theorem? Let's now look at or try to motivate this idea of working circuit problems in the frequency domain. And in particular, what we are wanting to do is, we've already worked some in the frequency domain. And how did we do that? When we had sinusoidal excitations or sinusoidal sources. Then we would wait until the transient was gone. And how long does it take for a transient to disappear? 5 time constants, roughly, rule of thumb. And that's not very long in a circuit in an electrical sense, typically. So that's why it makes sense to study sinusoidal steady state. But what we want to do now is be able to combine or look at both the transient and steady state behavior all in one. And we can do that by now looking at S instead of just isolating on j omega, or when we were dealing with sinusoidal steady state. We want to now allow for a more general frequency variable, which is this frequency variable S, and not just j omega. So here's our motivation, hopefully, for doing this. Suppose that we are given the following circuit. Given that circuit, maybe somebody wants to know how to find somebody says, I want to know what v sub 2 of t is. What would be your approach right now at this point in the semester? Pardon? So now what we would be doing is solving differential equations, right? We have a linear circuit. These R's, L's, and C's are constant parameters. We have a linear time invariant circuit. We can write the governing differential equations. How many differential equations would you expect to be surfacing on writing those? 2. It's a second order, so you could have 2 first order or 1 second order, depending on how you wrote those up. But now you have a second order differential equation or system of equations. You would now need to somehow find the solution to that coupled set of ordinary differential equations. And you could account for the initial conditions if they existed. And so we would then be writing 2 and to be generic, we could say integro differential, meaning the equations could contain integrals, they could contain differentials, and we would write 2 of those. If it turned out that one of those equations maybe it involved the current through that inductor, L, then we could use that inductor current to find V sub 2 by scaling it by R sub 2. And that's what we would probably be doing in the time domain. We would be isolating or trying to focus our attention on the inductor current and the capacitor voltage. And that might be what our equations would be written in terms of. Meaning if one of those equations involves the current, in what might typically be called the second mesh, the rightmost mesh, then we could say that V sub 2 of t is simply R sub 2 I sub 2. But that means that we must solve potentially this coupled set of differential equations. And we might then want to be looking at a homogeneous equation, a particular solution, and combining those, and now we have this complete solution once we know the initial conditions, and we can then find the answer that we need. Let's now look at this in the S domain. Here is our S domain circuit, and as general a case as we could place it, we would Laplace transform the time domain source voltage, and we're now going to call that capital V sub I of S. We would have our resistor, we would have our capacitor, and now if we needed to find that voltage across the second resistor, we would solve for capital V sub 2 of S, and then inverse Laplace transform, which we now are able to do to find our V sub 2, little v sub 2 of t. Where you might be starting to question what's going on or scratching your head is where we only had one source to begin with on this problem. And now we have three. What in the world happened there? These sources are arising or being introduced because of the potential initial conditions on our capacitor and inductor. And we can then incorporate those or integrate those into our circuit by introducing the appropriate type of initial condition. So here is what we want to do. We now might be asking, why are there voltage sources in series with the energy storage devices? And as I said, those are actually there so that we can actually account for the initial conditions on those very same energy storage devices. And the way to see that then is to go back and recall what I said you need to remember until you retire. One of the facts. And what is one of those facts? You need to know, or to be able to keep in mind, the relationship between current and voltage on at least these fundamental passive devices. Recall the current voltage relationship, and to begin with, let's just look at what we have for a capacitor. From Eli the Iceman, the ice part tells us what the capacitor relationship is. We have the current through the capacitor, I sub C, is now equal to C times the time rate of change of that voltage dropped across that capacitor. And what we're wanting to do then is show that if we now take that time domain relationship between current and voltage into the S domain, we can now figure out why we are having to deal with, or where these initial conditions are coming from. Remember what the Laplace transform looks like if we now Laplace transform this. The left-hand side is easy. That's just some generic time domain wave signal, I sub c, little I sub c of t, and that then Laplace transforms into just capitalizing the I. So I now have capital I sub c of s, that's the Laplace transform of the current. The c is not a problem, that's constant, and we don't need to worry about what that does when we Laplace transform a constant, that slides through. The only thing that we really need to worry about is the Laplace transform of a derivative. And that's why we studied that, which is we have S times the Laplace transform of the function, which in this case is the capacitor voltage, minus the initial condition on that voltage. Let's now distribute that C throughout, and we have SC times V sub C of S minus C times V sub C of 0 minus. And a lot of times we're used to seeing this in terms of V is equal to IR, or V is equal to some impedance times I. So let's write it in terms of V times an impedance. If we solve for V sub C of S, the capacitor voltage, it actually is made up of two pieces. We can move that initial condition term to the other side of the expression and divide both sides through by SC, and we then end up with 1 over SC times I sub C of S, plus we have C divided by SC, or we now have the initial condition, that's the time domain voltage at 0 minus, divided by the complex frequency variable S. And what we can extract from this relationship is that this is now what we can consider to be the impedance of a capacitor. Instead of 1 over j omega c, we've now generalized j omega into S. We now have 1 over SC. Anytime we have a capacitor and we want to go into the S domain, if we don't worry about initial conditions, we can just replace those C's with 1 over SC's. And that's now the impedance of that capacitor. If we need, or if we have initial conditions present, then we need to account for those in this particular manner. Meaning the voltage dropped across the capacitor is a combination, is a series combination of the impedance of that capacitor and a voltage source due to the initial condition, where this voltage source is looking like a constant in the time domain because it's some constant over S, and that's what a U of t transforms into, a U of t in the time domain. Are there questions on that? What happens when we look at resistors from the time domain into the S domain? There's our governing current voltage relationship of a resistor, which if we transform that equation into the frequency domain, it doesn't look too much different, does it? So this one now in the S domain, these resistors now carry over into the S domain unaltered. So to have some more excitement come back in, apparently if the lecture is not exciting enough and you have the caffeine now, we can look at the inductors. The inductor is similar to the capacitor because it now is governed by Eli. Yes? So Eli tells us V is equal to L di sub L of t dt. And we can do exactly what we did before. If we now transform that into the S domain, we have this V sub L of S is equal to L times S I sub L of S minus I sub L of 0 minus. And we can now distribute that L among the two terms. And we now see that the impedance of an inductor is simply S times L And the initial condition term now has this negated combination of L and the initial current through that inductor. And now if we needed to, how would we solve for v sub 2 of t in this circuit diagram? Now hopefully you feel a little bit more comfortable about where those voltage sources come from. Those appear because of initial conditions on those energy storage elements. If the voltage across the capacitor was 0, then this would be a short, and we would simply have the impedance of the capacitor, which is 1 over SC. But we now have incorporated the series sources with the impedance of the capacitor and the inductor, so that now maybe we haven't changed. Question? Okay, so the question was, how do we know that we want to use a series voltage source for the capacitor or the inductor, or could we use a parallel current source? And we'll cover that a little bit later, but in this case, what I was looking at is, we're very comfortable doing mesh analysis. And what I did is I preserved the meshes by keeping those two initial conditions in series with the impedance. I didn't change the topology of the circuit very much. I now just introduced a series voltage source in these branches. And now I still have two mesh currents that I can solve for. So in this case, the reason I preserved or went with voltage sources in series with the impedances is so that now if I want to solve for maybe I1 and I2, I can now, if I find I sub 2 of S, I can multiply it by R sub 2, and that will give me V sub 2. And maybe I just felt more comfortable doing mesh analysis. And so I preserved that two-element mesh analysis problem by introducing the initial conditions in series with the impedances. Question? So now what we need to do is we need to make sure that the polarity is correct. And we'll talk maybe a little bit more about that, but let's just do it for now, since the question is here. If we wanted the polarity, here's what we did. We have this inductor in the time domain, and we are using the passive sign convention to do that. So here is our time domain picture. What we ended up with in the frequency domain is we said, the voltage dropped across the inductor in the frequency domain is going to be between these 2 points. It has to contain both elements, the impedance element and the source. That's the total voltage dropped across the inductor. That's V sub L. So let me say this is now V sub L of S. This is not too difficult. That's the impedance. That's SL. But to be consistent, my current needs to be right there, I sub L of S. Now, the way that I like to do this, just to make sure that I'm doing it properly, is I just write a KVL equation around that hypothetical mesh. Meaning, now I can say that if I do that, I have a minus V sub L of S, and then I come back and go towards the right through SL, and I now say plus SL I sub L of S. And now I don't, maybe I don't remember which way the polarity goes. So that I now say, here's plus minus, and I know that the value of that is L I sub L of 0 minus. And now I'm coming in through the plus sign. And I say, okay, does that look like what it's supposed to? And it doesn't, does it? Because I need for V sub L of S, if I move that to one side, I need that to be S times I sub L minus L I sub L of 0 minus. So I need to change this to a minus sign, or I needed my polarities to be minus plus relative to the direction that I had defined my original voltage and current in that circuit element. Is that making sense? Meaning now I know where to put my impedance, and now I know how to indicate or mark my polarity in my voltage source that's in series with that impedance of the inductor in order to account for the initial condition. Question? So these initial sources, what are they? Are they DC? It's really whatever they need to be so that they give us the appropriate energy in our circuit. In this case, what did we, well, we had two different scenarios. If we go back, if you now looked at the capacitor's initial condition in this configuration, what does that look like in the time domain? This v, little v sub c of 0 minus over s, what would that correspond to in the time domain? That's a constant, isn't it, of magnitude v sub c of 0 minus. What's the inductor's initial condition look like in the time domain? That's an impulse. So now we would have to have an impulsive source for the inductor to give us the voltage that we need, whereas for the capacitor, for a series voltage, we need just a constant-like source. So it depends on how we are representing those as to how they appear in the S-domain circuit. What we will do subsequent to today's lecture is to work our way through this process of showing how to adjust or define the appropriate polarities. Here we were dealing with polarities in the voltage sources. We will then, in probably the next lecture, talk about how we integrate those with current sources. And then we have to worry about the direction of the current arrow consistent with our overall inductor current or capacitor current. Did that help answer your question? Is that okay? Let's look at, so in this case, we would simply find, so if we wanted to find V sub 2, now all we have to do, but it's actually made our job a little easier because now what we have to do is simply what we are used to solving with purely resistive circuits with some sources. We have two meshes, and now we treat these impedances just like generalized resistors. And we have then the two impedances seen by I1, we have three impedances seen by I2, and because there are no dependent sources, we could actually write these equations down by inspection. It's just now we have to deal with these, the algebra including complex numbers, S terms. Meaning, maybe I should just do this. What would it look like if we now solved for or set this up? We would have, let me say, the way I've set it up, I would find I sub 2 of S. One of the mesh currents. And determine V sub 2 of S from that I sub 2 of S. If I wrote this in a matrix structure, I'm probably not going to have enough room. Not sure why I wanted to put I sub 2 first. It shouldn't be. Let's make that I sub 1. I won't be able to squeeze everything I need into that right-hand column, but let's try anyway. Here's my structure. I have two unknowns, I1 and I2 of S, capital I1 of S and capital I2 of S. The matrix that pre-multiplies my unknown vectors, my unknown vector of currents, I sub 1 and I sub 2, what are the dimensions of that matrix? It's 2 by 2. I have two equations in two unknowns, and my left-hand matrix is going to be a 2 by 2. My right-hand column is simply going to be a column, and it will be made up of two different rows. Now that row may be populated with a lot of different terms, but it's just one row. What's in the 1-1 entry of this impedance matrix? In this case, what do I have? I really have a matrix version of Ohm's law. I have Ri equals V, a generalization of that. Now this left-hand matrix is a 2 by 2. It's an impedance matrix. It's Zi equals V. So everything on the right should look like voltages in the time domain. What's my 1-1 entry in this impedance matrix based on this circuit? And I said we could do this by inspection. Did you do this in 220? The inspection way of putting it into a matrix? Yes, no, you can be honest. No. Well, here's the way. So I'm looking at what's associated with the left mesh, the mesh associated with I sub 1. And I say, what impedances touch, or what does I1 touch in terms of impedances? R1 and 1 over SC. It only touches two impedances. The sum of those I put in the 1-1 entry. Meaning down here in my matrix, I now say that this is R1 plus 1 over SC. That's my 1-1 entry. Now I come back. I'm sorry, everybody, you still are on Dramamine from spring break probably, so it's probably okay. Sorry. Now to find the off-diagonal terms, which in this case is the 1-2 entry, we look and see, is there any impedance that's sharing I1 and I2, or is there any impedance that's seen by both I1 and I2? And there is. It's the 1 over SC. Well, we write that impedance down, but we negate it. It's now going to be a minus 1 over SC in the 1-2 entry. So we write that down. So this is now minus 1 over SC. That was the impedance shared by I1 and I2 in the circuit. Now to find the source terms in the right column, the 1-1 entry there, now we look back at our circuit and we say, or we ask the following question. We come back to our circuit and we say, okay, I look at all of the sources that are touching I1, and I say, does that source enhance or does it help increase I1, or does it go against I1 if I made it more positive? Meaning if I look at V sub I of S and I said, if I increase V sub I of S, will that serve to make I1 larger? Yes, it's trying to push I1 out because of I1 coming out of the positive. What about the source due to the capacitor's initial condition? If I increased it, would it impede I1 or enhance I1? It would impede. So it's going to come in with a negative sign. If it helps, it's a positive. If it distracts or impedes, it comes in with a negative. Meaning on the right-hand side, for the I1 mesh, I now have V sub I of S minus whatever the initial condition was, which in this case for the capacitor was this V sub C of 0 minus over S. And that's the top row. That's the first equation. Questions on that? How that was obtained? With that strategy in mind, what's going to be in the 2-2 entry of my impedance matrix? Yeah, R2D2, is that what you're wanting me to say? No. That's what you were wanting to hear. How many terms do we have in the 2-2 entry? I2 touches three impedances. It touches 1 over SC, SL, and R sub 2. Those three terms go in the 2-2 entry of I sub 2, or in the second row. What's shared between I1 and I2? 1 over SC, as before. And what about helping or hindering I2? Does the capacitor voltage source help I2? If we increased it, it would, wouldn't it? What about the inductor's initial condition, the way it's now coming into this expression? It also would enhance I2. So those both come in with a positive sign, and we're left then with the following. We have in the 2-2 entry all three, which there was an R2, there was an SL, and there was a 1 over SC. Shared between the two was SC, 1 over SC, and that comes in with a negative sign. And then we have the two sources. Told you I wouldn't have enough room, but that's plus L I sub L of 0 minus. Questions on that? And if you needed to find I2 or I1, you could simply solve for I2 or I1 in this vector case. And it could be a ratio of determinants. Does everybody remember Kramer's rule for solving matrix problems? What? You remember how to use your calculator. Well, if it does symbolic algebra, it will perform that analysis. Meaning if we wanted I2, let me just go through it. It's now going to be a ratio of 2 by 2 determinants. Here I copy down the first column because I2 impacts the second column. The second column I actually replace with the right-hand side. And you better be able to remember how to do a 2 by 2 determinant. And now the denominator is just the impedance matrix determinant. And now we have this transfer function for I sub 2, a ratio of polynomials in S, by simply doing the product of the diagonals minus the product of the off diagonals. That's a 2 by 2 determinant, and we're done. And that was a fairly just turn the crank process to find the transfer function between the input voltage V sub I of S and the output current, let's say I sub 2 of S. We now have that relationship in terms of initial conditions and the forcing function. Questions on that? Let's look at a different example. Suppose that I now provide you with the following. Here's V sub 1 of t. have some very practical capacitor values. Let's say that this is the second capacitor, V sub C sub 2. There's my first capacitor, V sub C sub 1. I'll call this my second inductor, and this is my first inductor. That's a good question. Let's have it coming. So the question was, why did you not draw that line? So hopefully that's acceptable for you. And now I need to show you what V sub 1 is. Suppose that V sub 1 of t is u of minus t plus cosine of 5t u of t. This is what you could expect to see on your next exam. The first of 10 problems. Your second one would be a 10 by 10 matrix that you have to invert symbolically in terms of S's, right? Drop forms are going to be available after class. All right. Now, what does V sub I or V sub 1 of t look like if we had to sketch that? I'll draw the easy part. Oh, well, you can make your cosine look better than that. What's that supposed to be? That's supposed to be cosine of 5t. And what's the other half? Well, that u of minus t, when is the argument of that u, of that unit step, non-negative? For negative time. When t is negative, that unit step is on, meaning v1 of t, actually this was easier to draw, I guess, has a magnitude of 1 from minus infinity up to 0, and at 0 we transition from a constant source to a cosine source. That's v1 of t. Questions on that? And here's our circuit. Now that we know how to incorporate initial conditions, we can look at this and say, okay, what's happening prior to t equals 0, and then what happens beyond t equals 0. We can draw our S-domain equivalent circuit and analyze it from that. Meaning it's a two-step process. The first step is what's going to happen prior to t equals 0. It'll be in a steady state condition because this current source is constant. That's 5. And this switch is closed prior to t equals 0. So this source will be active for t less than 0. This voltage source, likewise, will be active. It'll have a value of 1 for negative time. That's a DC value. This is a DC value. Now we can say, okay, what's going to happen if this circuit was in a DC operating condition? What happens to your energy storage devices? V is equal to L di dt and I is equal to C dV dt. We know that V is equal to L di dt. If our currents are constant, di dt is 0, so the voltage drop across the inductor is 0. Those will be shorts. Ice tells us just the opposite. I is equal to C dV dt. dV dt is 0 because it's constant, or we have constant voltages. So the current through that capacitor is 0, meaning it's going to open up if we have no current going through our capacitors. Is everybody clear on that? now we can re-sketch this diagram under the condition of t being less than 0 and try to determine what our initial currents are in those inductors and what our initial voltages are on those capacitors. Is that clear where we're headed? Let's now try to redraw that circuit for t less than 0. And that will allow us to establish initial conditions. We have a voltage source of 1. The first inductor is shorted. And I'm going to go ahead and explicitly show the disconnected capacitors. The second inductor is shorted. That switch is closed. And in terms of my variables that I'm looking for this current, I'm looking for this current, I'm looking for this voltage drop, and I'm looking for this voltage drop. And I guess I can label my resistor values. If those open circles on some of those wires are confusing you, simply erase them for now and just look at this all resistor network with a voltage source and a current source and ask yourself, how would I solve that circuit? There's all sorts of ways to solve it. The way that I solved it is I said, okay, let me just call this one of my nodes of interest, and I'm going to call that not V sub 2, let me call it V sub x. And maybe I just say that's my node A, and I'm going to write one KCL equation at that node. And if I can find the currents all leaving or arriving at that node, then I can solve for V sub x. And once I know V sub x, I can solve for everything else in that circuit. That's really the only unknown that I have if I think about it in this way as a node voltage problem. Let me now write KCL at A. I have this current going that direction. I have this current coming up, and I have this current going out. If that's the case, if I say, okay, my red currents all sum to equal the black current coming in, what's the current going from A over to the left in terms of my variables that I've identified? I simply need to look at the voltage dropped across the impedance between those. I don't really need to worry about that node between the resistor 1 and the resistor 2, since I can just sum those up and be done with it. And now I have those two resistors sum being 3. That's the current going from right to left horizontally. Going down through the 8 ohm resistor, the current is V sub x over 8, and those must equal the current coming into that node, which is 5. And the only unknown in that single equation is V sub x, and I can solve for that. Is it okay if I just write down the answer? It's really clean. Hopefully I've done the math right. 128 over 11. So you can see that I spent a lot of time making sure these numbers come out nice. That's V sub x. If we know V sub x, now we can solve for all of these unknowns. We can solve for the two currents. It's the same current. I sub L1 of 0 minus is just in the other direction. It's 1 minus V sub x over 3, which ends up being minus 39 over 11. Pardon? A nice round number. I sub L sub 2 is the same. And I can now find my capacitor voltages by writing some KVL equations if I want. Meaning if I do the left mesh and say I go up through the 1 volt voltage source, I have minus 1 plus I sub L sub 1 of 0 minus times 1 plus V sub C sub 2 of 0, and I'll find V sub C sub 2 of 0. I have then minus 1 plus I sub L sub 1 of 0 times 1 plus V sub C sub 2 of 0 minus is equal to 0. And if I have done the algebra correct, that ends up being 50 over 11. And finally, I could do, let's say, this KVL equation if I wanted to, and I could now say that I have minus, minus V sub C sub 1 of 0 minus plus 2 I sub L sub 2 of 0 minus equals 0, or V sub C sub 1 of 0 minus is twice the 39 over 11, negative. What I can now do is I can now, if I wanted, what's going to happen at t equals 0, this 5 amp current source is going to disappear. I can forget about that. And if I forget about that, if I didn't have any initial conditions, I would have a 3-mesh problem. If I wanted to preserve that, I could simply introduce all of my initial conditions as series voltage sources. And I have all my initial conditions. And I can now solve this circuit in terms of those 3-mesh currents. Is that clear? What if I now look at what's happening for t greater than or equal to 0? I now have my voltage source, which is now a pure cosine of frequency 5 radians per second. I have the impedance of my inductor, which is SL. I have its initial condition, which is L times the initial current. And I have my 1 ohm resistor. I have 1 over SC, and I have my voltage source, for that capacitor. Likewise, I have this inductor, SL. It had an L value of 3, a source voltage of 3 times L, where 3 times I sub L of 0. Then I had the resistor of 2. I have the 8 ohm resistor. And I have this last mesh, which was a 5 ohm resistor, a source due to the initial condition on the capacitor, which that capacitor is then minus 78 over 11s. And now if I labeled this and said this is I1, this is I2, and this is I3, as long as those are all going in the same direction clockwise, I can use my inspection trick or technique that we just talked about. And now what's my impedance matrix dimension? It's a 3 by 3. And I will have all of these sources incorporated in the right-hand side. Questions on that?